So everybody is ready. So we start our first contributed talk session, and as far as I see, it is going to be under the moment banner. The first talk in this session is pre-recorded. The title is Partially Evaluating Symbolic Interpreters for All, and the speaker is Shangyin. Please start the play, and we are going to listen.
Is Shangyin. I'm an undergraduate student at Purdue University. Today I want to talk about our research paper on towards partially evaluating symbolic interpreters for all. This is a joint work with Guannan and Tiark. So first, let's review an important concept, symbolic execution. Symbolic execution is a technique widely used in many areas, including program analysis, verification, automated testing, etc. Symbolic execution execute programs with symbolic values and collect pass conditions for the solvers. The simple example here shows that if we do a symbolic execution on this small piece of program, we would obtain the following pass conditions in 3 different passes. Then the SMT solver is able to figure out what concrete values leads to the corresponding pass. There are a few ways to implement symbolic execution engines. First, many symbolic execution engines are implemented as interpreters. Interpreters are close to semantics and easy to implement, but it has an interpretation overhead. A more performant way is through instrumentation. Instrumenters are often more performant, but less flexible. And it is also unclear how instrumentation relates to the semantics of symbolic execution. To find the sweet spot between performance and semantics, we propose to build symbolic execution compilers. Before I get to know how to build symbolic compilers, I want to quote Tiark and Boddick here. Building a symbolic compiler is often the most difficult aspect of creating solver-aided tools, especially for general-purpose languages. So building symbolic execution compilers are really difficult. Why don't we just build a definitional interpreter and turn it into a compiler? Here is another important background. We can actually turn an interpreter into a compiler for free using multi-stage programming and partial evaluation. In the 70s, Futamura came up with this beautiful observation called the first Futamura projection. It says that specializing an interpreter for the given source code yielding an executable. Suppose we have the interpreter for the language L. It expects the source program in L and the input to the source program, and it returns the output of the program. If we partially evaluate this interpreter interp to the source program, we can actually obtain another program called interp L, suppose, that takes the input of the source program and returns the output. Then this process could be seen as compilation. We obtain a compiler from the interpreter for free. To achieve or implement this first Futamura projection, we use the Lightweight Modular Staging framework in Scala, which is a library for multi-stage programming. In fact, our previous work on compiling symbolic execution with staging and algebraic effects gave a prototype symbolic compiler by partially evaluating the symbolic interpreter for nondeterministic symbolic execution. By nondeterministic, we mean that the symbolic execution forks at the symbolic conditions and execute both feasible branches nondeterministically. But a natural question to challenge this work is that if it's generally applicable to other variants of symbolic execution, or symbolic interpreters. And our answer is yes. In this paper, we explore 2 other famous symbolic execution variants, namely the Concolic Execution and backward symbolic execution, and develop the corresponding compiler by partially evaluating the symbolic interpreters. The figure presents an overview of our approach. On the top level, we have 3 but potentially more symbolic interpreters of different kind. The first interpreter, the non-det or non-deterministic symbolic execution interpreter, is presented in our previous work. So now, we first want to see how to develop this Concolic execution interpreter from scratch and fit the Concolic interpreter into our framework to turn that into a Concolic compiler. Before we really get started, what is Concolic execution? Concolic is the made-up word from concrete and symbolic. So Concolic execution execute programs both concretely and symbolically at the same time. Still using our previous example, now instead of having x and y being solely symbolic, we gave them two concrete values too. Let's say 1 and 5. Then the first if statement would go to the true branch under the concrete execution, and we track the pass condition just as what we did in the normal symbolic execution. Then after this execution finishes, we can negate the pass condition to generate new concrete values, which will be used in the next iteration. And this new generated value, for example, x is 2 and y is 1, guarantee coverage the other side of the branch. So if you use x is 2, y is 1, the program will explore the other branch of this if statement. The benefit of Concolic execution is that it somehow avoids the pass explosion problem of nondeterministic symbolic execution with forking. So this Concolic execution explores one pass at a time and guarantees coverage improvements iteratively. It is quite useful in practice. Now we want to show that our previous work to build the symbolic execution compiler can be applied here as well. Consider a simple imperative language that is similar to the LLVM IR. We have basic arithmetic instructions, assignment instructions, memory instructions, and control instructions like jump, conditional branch, or return. Let's see how to develop the Concolic interpreter and compiler for the small language step by step. We start with concrete execution. Here, we provide the signature of our concrete interpreters and omit the actual implementation due to the space limitations. It is quite standard and should be similar to the monadic interpreter everyone is familiar with. We also provide a executable reference implementation online, so feel free to try it. We use the state monad here for simplicity, where the state is a pair of concrete heap and stack. To obtain the desired Concolic interpreters, one very important observation is that for most instructions, symbolic semantics is independent from the concrete semantics. For example, under concrete semantics, assignment instructions evaluate the value to be assigned and bind that with the identifier in the environment, in the concrete environment. However, since the value now can also have a symbolic representation, we would also need to execute this value or evaluate this value symbolically and bind the symbolic representation with the identifier in the symbolic environment, which is independent from the concrete environment. So before we do everything else, we must change the definition of our state. The concrete state now called C state, and we introduce additional symbolic state for the symbolic execution. The symbolic state S state contains a symbolic heap and a symbolic stack, which are mappings from the addresses or identifiers to their symbolic values. The symbolic state also includes a pass condition set, pass count, to keep track of the pass conditions. The state now becomes a tuple or a pair of C state and S state. Now we have the proper state to work with. We want to come up with the interpreter for symbolic execution. Here on the left, we showed an overview of our symbolic execution interpreters. You can see that here for assignment, what we're doing is that we are evaluating the value v symbolically using this eval vol_inst value instruction s, which stands for symbolic, and then we update the symbolic environment using this helper function, update syminf. So this whole thing is definitely independent from the concrete semantics. This is why we want to have the symbolic interpreters and the concrete interpreters separately for clarity and modularity. For control instructions, however, the symbolic and concrete semantics should be handled together. For example, jump instructions jump to another location in the program and should be only executed once. Let's see how to combine these two interpreters together. First, we define a few auxiliary functions. This delta or split function combines two monadic functions of the same source type and different result type to a single function that returns a pair of results. This function is good enough for simply combining two simple interpreters, the concrete interpreter and the symbolic interpreter, if the semantics is completely separate. However, if the instruction changes the control flow, like the jump instruction we discussed before, split is not enough. We combine the split function and the idea of callback value fixed point combinator to derive this split fix combinator. So f and g's here are the same as the argument of split. The third argument, ev, is a higher order function that takes two functions of the type a to m of b and c. The first function provides the result of the base cases, the cases where no further care is needed other than simply combine two interpreters together. The second function of that type is a self-recursive function to handle the control and recursive instructions. So let's see how to define the final concolic interpreters using these combinators. Here is the concolic interpreter. It is quite simple. F and G's here are the concrete and symbolic interpreters for instructions eval inst C and eval inst S. And now we want to define this EV. For example, the instruction count BR conditional branch, which is similar to the if statement, has to be handled inside the function EV. So for this case, we first evaluate the condition C both symbolically and concretely and obtain the concrete CC and the symbolic SC. Then we want to update the pass condition using this update PC helper function. And after that, we can use the find block to retrieve the corresponding branch instruction list to be executed and use this for_m to apply the recursive interpreter rect on the desired branch list based on the result of the concrete condition CC here. So after we obtain the proper concolic interpreter, we want to turn this concolic interpreter into a concolic compiler by staging using the multi-stage programming framework, LMS. First, we want to do a manual bending time analysis. This bending time analysis needs to distinguish the static part and the dynamic part. So static structures are resolved during the compile time, and we will not generate code for them. So namely, all the ASD of the source program are static. And for the dynamic parts, they're typically involved in the runtime computation, the real computation of concolic execution. So examples are states or input values. Here, we can annotate the dynamic parts at the type level for code generation in LMS. We use the notation rep of t to represent that the type t is staged. So other than the interpreter itself, the helper functions have to be staged as well to generate the proper backend operations and modify the state. After this very simple refactoring to turn the concolic interpreter into a staged concolic interpreter, we can use it to generate code for concolic execution. Together with the backend runtime, symbolic runtime, and the SMT libraries, we can further compile the generated code to an executable, and this executable will faithfully perform the concolic execution based on the semantics we defined earlier. To evaluate our performance, we developed a concolic interpreter targeting LLVM IR. We made changes to the previous non-det or nondeterministic compiler. We have to add support to separate the concrete and symbolic executions. We also have to change the backend to support this additional symbolic state. All the modifications are done within 500 lines of code change. Thanks to all the great functional combinators we can use to develop the interpreters in Scala. To measure the performance accurately, we evaluate the running time of an end-to-end run of a single execution or a single iteration of the benchmark programs and generate all the possible test cases using SMT solvers. SymCC is another very recent concolic execution compiler using LLVM's infrastructure to do instrumentation. We compare our tool with SymCC's Z3 backend. For fair comparison, we make sure that the input seed is the same and the generated test cases are identical. So we can see here that our concolic compiler has comparable for performance compared to SymCC on almost all the benchmarks. Now we want to discuss another interesting variant called call chain backward symbolic execution. So this variant is less famous in the Concolic execution, but it's also quite interesting. It is introduced in the paper called Directed Symbolic Execution to solve or optimize symbolic execution that want to reach a specific program location. To see what this variant is, here's another very interesting example program written in C. Our goal here is to find the concrete input to trigger the target function. As you might observe, the function f has 2 to the 4, which is 16 number of passes, induced by the if statement inside this for loop. So this if statement is basically extracting or testing each bits from the second argument b. After this loop, only one pass of those 16 passes may trigger the target function, depending on the first argument a. In the main loop, this function f is called many times, and under normal symbolic execution, every invocation of this function f has to explore all the 16 passes. And in the first 500 iteration of this for loop in the main function, all of the passes are not feasible because the first argument a or I is not 500. So this program is generally hard for forward symbolic execution engines to run, but CCBSE can handle this quite easily. How? So CCBSE executes function that contains the target function first, symbolically just like any other normal symbolic execution, and execute this function. CCBSE is able to obtain a summary of that function. The summary only contains the desired pass that leads to the target function, discarding all other irrelevant passes. Then we execute the functions backwardly following the call chain to the target, and update the summary for each function on that call chain on that line. So note that the call to the functions with summaries will only follow the path in the summary. And so after we traverse backward the call chain and we reach the entry function or the main function, this whole execution finishes. So in this example, as we first evaluate function f, we will get a summary that contains only one pass, because as we discussed before, only one pass is feasible. It's possible to reach this target. In the main function, the first 500 iterations of the for loop will call f, but unlike the forward symbolic execution engine that will explore all the 16 passes, since now we have the summary of f, these 500 calls to f only needs to explore that one pass. And all of which are infeasible because the first argument is not 500. And then in the next iteration, in the 501 iteration, when I or A becomes 500, we can reach the target. As you can see here, that this makes the overall execution much faster and easier. So how to build or implement CCBSE compiler? There are three major challenges we need to solve. So first, we need a forward symbolic execution engine to execute each function. And second, we need to schedule the order of function execution in a call chain backward fashion. And third, we need to track the summaries of each function and compose the summaries together. The first challenge is quite easy, as we already have the non-det symbolic execution interpreter, which is a forward symbolic execution engine. We can use part of that engine as a subroutine in the CCBSE compiler. So now we want to focus on the later two challenges. To schedule the order of execution of functions backward following the call chain, we will need to have the runtime call graph representation. So luckily, as a language we have right now only have direct function calls, we can compute the call graph at compile time statically by analyzing the static ASD, and it generates the static call graph into the generated code. Then we can add a runtime scheduler to execute each functions in our desired order in the backend. So based on all the information stored in the runtime call graph. Another key aspect of comparing CCBSE is how we compose the results or summaries. To keep the summaries of each executed function, we choose the simplest form and just use the result or return type of our forward symbolic execution evaluator. So this result type or return type is just a list of final state and the pass conditions for each pass. To concatenate passes or summaries, we have to modify the part that handles the call instruction in the forward symbolic execution interpreter. As you can see here, the left is how we handle the call instructions in the normal forward symbolic execution. There are a few minor technical details like the reflect function we have not covered, but like here you could see here that we directly call function f, fv, and the first s is state, vs is the argument. So now we can make this simple modification to have the desired case in the CCBSE interpreter. The only modification is that if the function called li f has a summary, we will call a backend function concat to concatenate passes from the summary. So in the concat function, we will obtain all the pass conditions from the summary, so all of those pass conditions will lead to the target function. We use the pass condition to get the execution of this function f so that we're not exploring other irrelevant passes. The result returned, this res, if it also contains the pass that leads to the target function, it will be used in the summary for the caller later. So although it sounds really easy, this is all we need to develop the CCBSE compiler. Of course, all the supporting infrastructures like the partial evaluator or the symbolic backend have to be slightly modified to fit all the previous changes. Despite of all the minor changes we made, the implementation of CCBSE, of this new CCBSE compiler, really demonstrates that the modularity and the flexibility of our approach. So instead of implementing a runtime support for concatenating passes and a standalone execution scheduler, our approach enables smooth integration for more complex semantics. Depending on whether the changes influences the operational semantics of symbolic execution, the modification can be made directly on the interpreter as the call instruction example, or on the backend code as the scheduler example. To evaluate our approach, we design a few small example programs that is similar to the motivating example before. We record the running time of the CCBSE compiler and also the vanilla forward symbolic execution compiler LSC. Since both symbolic execution compilers shares most infrastructures, the comparison is more fair. As the test programs are intentionally designed to be hard for the forward engine, we can see here that the CCBSE compiler is indeed more effective and can run much faster than the forward symbolic execution engine. To check out more details about each benchmark program, you can go to the URL above. There we provide more details about how to conduct the experiment and how to reproduce the results. We also made our code available in this GitHub repo. To make a conclusion, in this paper, we show that how to incrementally build a Concolic interpreter and add staging annotations to obtain the Concolic compiler. We also discuss how to apply the same approach to the backward symbolic execution, the call chain backward symbolic execution. The performance and correctness is supported by our simple empirical evaluations. Thank you for this presentation, and I'm open to other questions.
Thanks for the talk. Now we'll check the question tabs. No raised hands and no QA, but we have some. Oh, I see two speakers are on the stage. Then I'll ask some questions. What path condition do you use in the Concolic approach? Do you use the simple negation path condition?
Oh yeah. So that's a very good question. So we believe that the way we use the path condition is not is sorry, is orthogonal to our approach of building smart execution. So we actually explore two ways to like process the path condition. And the first way is to, like, once you get a new path condition, you just negate the path condition and query the SMT solver to get a new set of input. And another way is, I think it's introduced in a paper called DART. So basically what they're doing is that they collect all the path conditions and they will negate each of the path condition one after another after this whole iteration finishes, and then use the new generated like test cases to generate more to execute the program many more times and obtain more path conditions to get more concrete inputs. So we evaluate both, we like implement both approaches, and I think they both of the approach works in our compiler.
They are combined or you tested them separately?
Oh yeah, so like so in our evaluation session we only test the case where we explore one path and obtain all the possible concrete test cases along that path. We did not test the one that would like generate all possible test cases.
Thank you. Now,
Thank you.
more questions. Oh, the question on the QA tab. Great talk, thanks. You said that the second version required additional changes. Is it possible to define modular reusable components instead of modification? By Jonathan.
Yeah. Thank you, Jonathan. So yeah, I think for this question, the component that process the path condition is like not depend on the infrastructure of our compiler. So that means if you have another like let's call it a scheduler or processor for the path condition for another Concolic execution engine, it will be really easy to integrate that part into our compiler, because you can see that as a higher order scheduler that will use the Concolic interpreter or compiler as a subroutine that is not really like deeply, how to say, depend on our Concolic execution engine.
Another thing to add is I think it's definitely possible to, say, using algebraic effects or type classes to further abstract over some ad hoc strategy over our implementation. Although our current prototype just implement those modifications, but not using those advanced modular reusable components. But I think the answer is definitely yes, and that's kind of something we also want to further explore. Yeah, thanks for asking this.
Thank you. More questions? I do not see anything. So, what SMT solver did you use?
Oh, we use the STP SMT solver, but right now we're integrating the Z3 solver as well. Yeah.
Nice. So, if no one has questions, then let's thank the speakers again for the nice talk